Right, so the next section deals with factorization in graphs. So what is a factor? A factor of G is a spanning subgraph, right? So it's a subgraph with vertex set the same as the graph itself, and then it's either got all the edges of G or it's got fewer edges than G. Right, so it's pretty much a graph that you take and you keep it as is, but you just delete some edges. Now for K, a natural number, we say a K factor is a K regular spanning subgraph. So it's a spanning subgraph where every vertex has the same degree, and the degree in this case is K. Now remember, a one factor is a perfect matching because a one factor is a spanning subgraph, and it's got the matching edges as an edge set. So that brings us to the definition of factorability, right? So we say G is factorable into factors, G1 up until GL, if each GI is a spanning subgraph of G, right? And the sets of edges are pairwise disjoint. So each factor, if you look at each factor and you select two arbitrary factors, then they don't share any edges. So it's pretty much, you can view this as taking a graph and basically using L colors and coloring the edges with L colors. And you cannot color an edge, you can only color an edge with one color at a time. You can't use more than one. So you can basically see it as, in a way, as an edge coloring problem. So factorizing it is into L factors is equivalent to coloring the edges with L colors. Right, now if you throw all the edges of each factor together, you get the whole edge set of G. And we'll call F, we'll use this notation F to denote the factors G1 up until GL, and that we call a factorization of G. Now, if there exists a factorization of G such that each factor is a K factor, then we say G is K factorable. Right, so each factor is a spanning subgraph and is K regular. Now remember, if a graph is K factorable, then the graph is regular, and each degree is a multiple of each vertex degree is a multiple of K. Now, I mean, this makes perfect sense. If you're able to factor the graph into factors where each factor is a regular graph of degree K, then obviously it must mean that the graph has to be regular and its degree must be a multiple of K. Okay, so it's pretty obvious that. So if we look at this even cycle, every even cycle is one factorable. As an example there we've got C6. So if we look at C6, there's C6. So basically we can go and factorize that C6 into two factors, and we simply delete those edges there, and we can color it with a different color. Okay, that's my first factor, and the other factor, so that will be my G, that will be G1, that will be G2. Right, and so we can just delete those edges there. And there we've got my factorization, and they are pairwise edge disjoint, right? So if we go and put the two graphs back together again, you can clearly see that if you superimpose them like that, you can see you get your graph, original graph back again. Right now, I mean, we noticed that each factor is each factor is a one factor. Okay, right, just an observation. Every one regular graph is one factorable, and every two regular graph consisting only of even cycles is one factorable. All right, so that's pretty straightforward. So just a basic question: is every three regular graph one factorable? Okay, and the answer is no. There are some three regular graphs with no one factor, as we will actually provide an example just now. Is every connected bridgeless three regular graph one factorable? And the answer is no. We could just look at the Peterson graph. Right, so there's the Peterson graph, and let's assume to the contrary that it is one factorable. So this means that we can actually go and delete a one factor from G. So if this graph here is in fact one factorable, it means I can divide it into three factors, each of which is a one factor, meaning that this graph must have a perfect matching. And let's assume that the blue edges that we're going to add now is a matching, a perfect matching. So I mean, okay, so if we look at this exterior, cycle, if we look at that. That cycle there. You've got one of three cases. You could either have two matching edges lying on that cycle. You can't have three. Or you could have one matching edge that lies on that cycle, or you could have none. If you have none, then this has to be a matching. That has to be your matching, perfect matching, because all the vertices on the exterior cycle, they need to be incident with blue edge. Now in that case, if we remove that perfect matching, right, you've got two disjoint odd cycles. Now you have to further factorize this graph with another perfect matching, and again, this is not going to be possible because you could match those two vertices, match those two vertices, but then again you're going to get a problem either there or there. Okay, so that definitely cannot be factorized into a one factor. Okay, so that case cannot happen. Right, so the second case is quickly, if you have two blue edges on the exterior cycle, if you have two blue edges there, then because this vertex here needs to be matched, the only matching edge that remains is that matching edge there. So we have that scenario there. Okay, so all the vertices that are matched, that one is matched. Those are all the matched vertices. Okay, So we are left with how many, well, the unmatched vertices are obviously the remaining ones. And because this vertex is matched, we can certainly not use that edge there. So we must either use that edge or that edge. Right, now in the case of that edge being used, we've basically got this situation here. We can delete that edge there and replace it with a blue edge. So that vertex is matched and that one is matched. And so the only, this vertex now is the problem there. And you cannot match it with that. So either this edge must be matched, which it can't be, or that edge must be matched, which it also can't be. Alright, so that case definitely cannot hold. So the only possibility there is for basically for that to hold there. Okay, so you need a blue edge there. Alright, so again, you cannot have a blue edge there, can't have a blue edge there. The only other option is for us to have a blue edge there. So then all the edges are matched. Now all the vertices are matched. So then if you were to delete your blue edges and see what situation you have, what have we got here? We've got two disjoint copies of C5, in which case you again cannot factorize that any further into one factors. Right, so then again the last possibility you have is there's only one matching edge on the exterior cycle, and then you need all these remaining edges here to be blue. And in that case, what's going to happen there, so that's covered, all those vertices are covered, that one's covered, and those two there are covered. So again, we cannot have a blue edge there, so we can't have a blue edge there, and we also can't have a blue edge there. So again, you cannot form a matching, perfect matching there. Okay, so it's pretty straightforward that Peterson graph is definitely not one factorable. So therefore, cubic graphs in general, they're not necessarily one factorable. This is a counterexample. Right, so the first theorem here, if G is a regular bipartite graph, then G is definitely going to be one factorable. Right, so recall that when we looked at matchings, we said that a regular bipartite graph has a perfect matching. We use that Hall's condition to prove that, remember. So we can generally, by induction, prove that if a bipartite graph is R regular, then it is one factorable. So if you look at let G be a R regular graph, and we can apply induction on R. Now if R is 1, then obviously G is a one factor itself, so it's one factorable. In fact, it's got one factor, and that factor is a one factor. Right, and then again you go from there. If R is bigger than or equal to 2, right, and we remember that this graph G must contain a perfect matching by that previous theorem I talked about. So therefore you consider the graph G minus the edges from that perfect matching. So you delete those edges of that first perfect matching. Now the resulting graph is going to be still a bipartite graph, and it's going to be R minus 1 regular. Applying our induction assumption to the R regular new graph, that graph can be factored it has a one factor, and it's one. Yeah, it can be factorized into one regular factors. And how many such factors will we have? There will be r minus one such factors. And then throwing, so you label those factors F2, F3 up until FR, and then you just throw F1 in, and that will be a factorization of the desired property. And this is a nice little application of one factorizations of KNN corresponding to Latin squares. It's nice to go and read. So remember, Latin square of order n is just an n by n array in which each of the numbers 1, 2 up until n appears in each row and each column exactly once. So you can basically model this with this one factorization. In this example here, where you look at K33 and you look at you label the vertices of each partite set with A, B, C, D, E, F respectively. Then we connect A with D in the first matching. And we assign the first matching with a number 1, and you can see there's the first matching there, and the second matching we assign number 2, and remember there's a number 2 edge between E and A, there between D and C, and there between F and B, and then the third matching, which we assign the number 3. There's a number 3 edge between F and A, and there's a number 3 edge between D and B, and again there between C and E. Okay, so that's a nice little extension of this factorization concept to Latin squares. Right, that brings us to the theorem that the complete graph on an even number of vertices for all natural numbers k is one factorable. So we just need to show that we can in fact factorize a complete graph on an even number of vertices in that way. Now there's just this little algorithm that they use to do that. It's very simple in fact. Right, we take the complete graph on an even number of vertices, and we draw it those vertices, we group them as a regular 2k minus n-gon, and we place V0 at the center. And then what we do is we factorize the graph as follows. For indices I from 1 up until 2k minus 1, we let Fi be the one factor whose edges are firstly V0 Vi and all edges drawn perpendicular to V0 Vi. And then this factorization will be a one factorization of K2K. Okay, perhaps it's just better to actually go and illustrate this with a drawing. Right, and if we look at this drawing here, if you look at this drawing here, so what you do is there, you've drawn this in this particular case, this is K, that is K, how many vertices have we got? We've got 6. So that's K2 times 3, okay, as an example. And then what you do is basically you draw it as an 2k minus 1, which in this case is 5 n-gon. Right, so you draw that, you basically group the vertices in that way, and then you place the V0 at the center. Okay, and then you, in each factor, you just take the edges that are perpendicular to that edge there. And those edges will only be those edges there. Right, so that first edge is V0, V1. Right, then you take V0, V2, and you look at all the edges that are perpendicular to that edge there. And then the next one you move, you look at V0, V3, and you run through all of your indices I till you get to the last I. Right. So just in general, if you look at K2K in general, right? Then just go and count the number of edges here. So here we've got counting that number of edges. That is going to be it's going to be 2K minus 2. You're subtracting those two vertices there. Divided by 2, and then you add that edge there. So you're counting, that's the number of edges that you're counting. Okay. Right now, and how many such cases are there? Well, you're going to run through. That's going to be V1. And how many vertices have you got to run through? You've pretty much got to run through 2K minus 1 cases. So in total, how many edges do you have? In total, you've got 2K minus 1 cases. And in each case, this is how many edges you've got. Right. So go and work that out. You get that is a half times 2K. And that is pretty much going to be, it's going to be 2K combination 2. Right, and that is going to be how many? That's going to be the size of M2K. All right, so you're covering all the edges with that algorithm, and those edges are all disjoint the way you choose them. And it's pretty much a case of that perpendicular line or edge, you keep moving it, and every time you move it to a different vertex, you are covering all those edges without the risk of repeating edges. Right, so that brings us to the next just point. If G has even order n and the graph is n minus 2 regular, then G will also be 1 factorable. And the way you see it is, if a graph is n minus 2 regular, it's basically the complete graph on n vertices minus a perfect matching. Okay, and basically using the previous theorem's algorithm, you can then, using that exact same factorization, you can factorize the remaining graph, which in this case is G, into factors f2 up until fn minus 1. Okay, so I mean that's pretty straightforward. If a graph is n minus 2 regular, it is immediate. You can find it from Kn by deleting a matching. Right. So going back to that argument there, you take Kn and you factorize it like we did here, but deleting this first factorization's edges, the perfect matching there, that will give you your K minus, that will give you G, right? And then G, you just factorize the remaining edges in that way. Okay, so it's pretty straightforward. Right, now the next type of problem is quite interesting. So what is the smallest that I can make the degree of a regular graph? so that every regular graph of that particular degree and bigger than that is one factorable. All right, now this question is a sensible question, because if you look at let's look at R equals to n minus 1. Okay, now if you look at every graph of every regular graph of degree n minus 1, every regular graph of degree n minus 1 is pretty much going to be kn, right? And we know kn, we can factorize kn such that each factor is a one regular graph. Okay, so G is going to be one factorable, right? So this number that we're interested in does exist, right? So the question is now, if R is n minus 1, yes, then every graph of every regular graph of degree n minus 1 is definitely one factorable. Now the question is, how small can you make this R? Let's take R to be n minus 2. If you look at a graph of degree, or regular graph of degree n minus 2, then by the previous theorem again, it is also one factorable. Okay, what about R equals n minus 3? How small can you go? And it turns out that we have the following results that were obtained. Before we actually get to the main result, they have this conjecture here, which is called the one factorization conjecture. If a graph is even order and R is at least the order of the graph divided by 2, then every R regular graph of order n is one factorable. So this is a conjecture. But it turns out that this theorem here, they prove that if G is even order and R and if G is an even order and is R regular, and R is at least the square root of 7 minus 1 over 2 times n, then it turns out that G is one factorable. Okay, so that's pretty interesting. So the question now is, square root 7 minus 1 over 2 n is bigger than this value here. So the question is, can you improve that bound? In other words, can you make it a little bit smaller? Okay, so this bound, the question is, can we make that bound smaller? And the answer is no, because look at the example, if you take 2k n over 2's, the union of 2k n over 2's, this graph is always going to be n over 2 minus 1 regular. But if n divided by 2 is odd, then you're sitting with a union of two odd components, right? And this is never going to have a one factor. So you cannot factorize it in that particular case. So the answer is, well, in that particular example, we have a regular graph that n over 2 minus 1 regular graph that is not one that cannot be that's not one factorable. So therefore, this bound, if it is true, this conjecture, that will be the best we would be able to do. Okay, so that brings us to the next theorem, which is Peterson's theorem. Now, just an observation, which is very easy to see. If G is two factorable, that means G can be factorized into factors where each factor is a 2 regular graph. Then obviously G is going to be 2k regular for some k, right? Because if G is factored into into two regular graphs, if I throw together all those graphs with their edges, it's going to give me the edge set of G. And if there are if each vertex in each one of the factors has degree 2, and we throw all those factors together, if each vertex has degree 2 in each one of the factors, then how many, if there are, say, k factors, then adding it all up, each vertex will have degree 2 times k in the graph that I get if I throw back all the edges. So it's that's pretty straightforward to see. So if G is 2 factorable, then obviously G is 2k regular. That's quite obvious. However, it turns out that those two statements, I can put an if and only if between them. In other words, a graph G is 2 factorable if and only if G is 2k regular for some k. Okay, so to prove that theorem, all we need to do is we need to show that if G is 2k regular for some k, then it has to be 2 factorable. Right, so to prove this, let's assume that let G be a 2k regular, let G be 2k regular, and let E be an Eulerian circuit. Now remember, in a circuit, vertices can be repeated, but edges are not repeated. And E is going to contain all the edges because it's Eulerian. Okay. Right, we define the vertex set of G as follows, and then what we do is we're going to construct a bipartite graph. Right there we've got the vertex sets U and W, and basically what we do is these U's correspond to the V's, and these W's also correspond to the V's. Okay, so it's just basically the vertex set of G that I take and I just duplicate it. And now what I'm going to we're going to do and the edge set is going to be defined as, what you're going to do now is you're going to join the edges between, you're going to join the vertices between U and W in a specific way. And the way you're going to do it is you're going to join UI to WJ. Okay, we join the ith U to the jth W. If Vj immediately follows Vi on this Eulerian circuit. Remember, the U's correspond to the V's and the W's correspond to the V's. So there's U and W. Now you look at your circuit E, and your circuit basically circuit goes there. Eventually it comes to Vi, and then if Vj comes straight after, immediately follows Vi, then what you're going to do is you're going to join UI to WJ. Okay, that is how this bipartite graph works. Now, one thing that we need to notice about this bipartite graph is that it is regular. And why is that? Note that G prime is K regular. Why is it K regular? Remember, each vertex in G has degree 2K. Right, so if you look at Vi, right, so somewhere within the circuit, you're going to come in there, then you're going to go to Vi, right? Then what's going to happen then is you are going to again leave. You're going to leave. Okay, and then again, somewhere along the line, you're gonna again come in, and then again you're gonna leave. Right, now, just for now, just note that this vertex comes straight after VI in the Eulerian circuit. This vertex comes immediately after VI in the Eulerian circuit. So again, for each, we have this alternation between the red and the blue edges, right? So basically, this process is going to carry through right up until the end, and you're going to eventually come in again, and you're going to go out again. And when you go out, that vertex comes immediately after, right? So it's this vertex here. So if you go and count the blue edges, because each vertex has degree 2k in G, if you go and count the blue edges, the way you construct your bipartite graph, that clearly adds up to k. So this bipartite graph is k regular. So thus G prime it has a 1 factorization. And we can call this 1 factorization F, right? So there are my 1 factors. Right, so let's define a permutation on each one of these 1 factors. And the permutation works as follows. We call it alpha subscript R. Okay, now what it does is it maps this integer I, it maps this natural number I to J. If UI is adjacent to WJ in the edge in the graph G prime, so that is an edge in G prime. Now, is this a permutation? And the answer is yes, because FR is a 1 factor. Right, so this function is going to be 1 to 1 and onto, so it is a permutation. Right, so what we can do is express alpha R as a product of disjoint cycles. Now this is a result in abstract algebra. Every permutation can be expressed as a product of disjoint cycles. All right, so we claim that none of these cycles only have none of these cycles can be a 1 cycle or a 2 cycle. In other words, each cycle must be at least a 3 cycle. So what happens if one of these cycles is a 1 cycle? Then for some I, alpha R will map I to I. Implying that U1 W1 is going to be an edge of G prime, and this is going to imply that in the Eulerian circuit, V1 is going to come straight after V1, and this is impossible. Okay, then just check that there are no 2 cycles. Some cycle is a 2 cycle, then for some I and J, we have that this permutation sends I to J, and this permutation also sends J to I. Right, so this will imply that VI comes straight after Vj on E, and vice versa. All right, so basically Vi comes straight after Vj and Vj comes straight after Vi. But this will imply that that an edge is repeated. All right, and again, this is impossible. As edges are not repeated. All right, so hence each cycle has at least 3 indices. Right, now if you go back to your original graph and you start drawing edges, remember now your permutation has at least, each permutation has at least 3 indices in it. So now what you do is you join, if you just look at index 1, then index 1 by the permutation gets sent to another index. Call that index, say 2 as an example. And then index 2, because there's at least 3, gets sent to, say, index 5. Let's call it. And then for argument's sake, index 5 gets, because it's a cycle, gets sent back to index 1. Right, and this is a permutation, it's 1 to 1 and onto. So basically in this way you can now go and construct within the graph U, you can go and for each one factor you can go and construct a disjoint union of cycles. Okay, but remember U corresponds to the actual graph G. Right, so basically if you take all the cycles within each permutation corresponds to a one factor. And if you take all the cycles which have at least 3 indices in them, and you group them all together, each one of those cycles corresponds to a blue cycle that I've indicated here as an example. So you get all these blue cycles, and they are vertex and edge disjoint. So you get all these blue cycles, and now these blue cycles correspond to the graph G. The blue cycles are actually inside of the graph G. Now we just need to make 100% sure that the edges for each factor, the permutation corresponding to that factor, we don't have a common common edges. So let's say, for argument's sake, in the first one factor, we call that, remember, we call that F1. Let's say, for argument's sake, that in F1, this U1 that we talked about here gets sent to W2 as an example there. Right, then remember, we're going to join U1 with U2 there in that particular permutation. Now let's say F1 and F2 share the edge U1, U2 as an example. Then in F2, that U1 is also going to be joined to W2. So F1 and F2 both share this red edge, which is that edge there, but for each two factors, we have that they're mutually edge disjoint, so we cannot share edges in that way. So for each permutation is going to generate cycles in G on the left partite set, and all these cycles are going to be edge disjoint. All right, so this is going to imply, that's going to imply that G is going to be factorizable. Remember the bipartite graph that we constructed? We said it's k. It has a k factorization, right? So right. Remember we said the bipartite graph G prime that we constructed. We said it is k regular, and therefore it has a 1 factorization. So therefore, I'm going to have exactly k factors, and for each one of those k factors, each vertex in U has got two blue neighbors, as we've explained there. So if you've got k, if you've got k factors, and each vertex in U has got two blue neighbors in each one of the factors, and none of the blue neighbors can be shared, as we've explained. We can't have shared edges. It means that throwing all these two factors together is going to yield vertices of degree exactly 2 times k. So you are going to get all your edges as well if you put all of these blue cycles together. All right, so basically that's going to imply that your graph is going to be you're going to be able to factorize your graph into two factors. Okay, so that's that theorem there. Now just another type question. Can we factorize every 2k regular graph G into two factors, each consisting of a prescribed number of cycles? Right, so can we put restrictions on the number of cycles that we get? And this is an example of the following definition. We say a factorization of G is a Hamiltonian factorization if each factor is a Hamiltonian cycle of G. Right, so that's an example of where you limit the number of cycles that you have in each factor. Now we say a graph is Hamiltonian factorable if it has a Hamiltonian factorization. Right, and this is just another theorem that corresponds to the concept of Hamiltonian factorization. Okay, so this theorem says that if you have a complete graph on an odd number of vertices, it is Hamiltonian. It has a Hamiltonian factorization. Okay, that you should just delete that just delete that one factorization. It has a Hamiltonian factorization. Okay, so it means that we can factorize it into factors where each one of the factors is 2 regular and it is a Hamiltonian cycle. Right, now again, I'm not going to go through that much detail, but the argument is similar to the one we used, the algorithm we used to prove the case for a complete graph on an even number of vertices. Remember, we proved that that is one factorization that can be factored into one regular spanning subgraphs. And what we do now here is a similar type argument. We again draw the vertices in a very specific order. But now what we do is we place we label the vertices V0, V1 up until V2K. And then what we do is we place V0 at the center, just like we did previously. Okay, and then what we do is we look at these 2 edges here. We include in each factorization those 2 edges. And then the remaining edges we choose as follows. We choose the edges that are parallel to this edge or parallel to that edge there. So these are basically these edges. So you start off with that edge and then you just choose all edges that are parallel to that edge there. And then what you do is you choose that edge there and you choose all the ones that are parallel to that particular one. And then what you do is you move on. You still have your center there. And now we've taken care of that vertex and we move on to that one there, which is that one there. You include those 2 edges there. And then what you again do is you start with the next vertex. And then you choose all the edges that are parallel to that edge. And then you choose the next edge there. And you choose them that such that they are parallel. Now the first factor and the second factor as an example here are all edge disjoint because of the way that you've drawn your vertices. Okay, and then you carry the process through. So we've covered that vertex. So it's a cyclical thing here. So we covered that one, and then we go on to the next one, which is that one there. You include those 2 edges, which are these edges. And then that edge you identify, and then you choose subsequently all the edges that are parallel to that one, and you choose that one there, and all those edges are parallel there. And you carry this process through until you have you've covered all your vertices. All right, but again, you're going to stop there because carrying on, you're just going to generate one of the previous cases there. So you're going to, right, so you're going to pretty much go from there to there to there. Okay, now again, as an exercise, go and look, just make sure that you're covering all your edges. And we've chosen the edges so that they are disjoint. But the edge counting is quite straightforward because for each factor you are counting how many edges. You're counting 2k plus 1 edges. Okay, so counting the number of edges for each factor, you've pretty much got you counting 2k plus 1 edges. None of the edges are repeated in each between factors. And then how many times are you doing this? How many such factors are there? Well, you're moving through k. Right, so there, 1, 2, 3, 4. Okay, so that is, in that case, that's k, right? So that you can again write as 2k plus 1 multiplied by k. Sorry, not well, you can write it multiplied by 2k over 2, and that is just again That is 2k plus 1. Choose 2, which is exactly the size of k2k plus 1.